Okay, let's walk through matrix vector multiplication. So, if you have some matrix A that's m by n, and you have a vector x that's an n vector, then you can multiply them together and you get a new vector y that's also an n vector. And each individual element, the ith element of yi, is going to be equal to the sum across some k of aik xk, like this. From k equals 1 to n. So I find it helpful, the book actually doesn't do this, but I find it helpful to, when I'm drawing these, to draw them out where I'm going to put A on the bottom left, and then I'm going to put X up here, and then I'm going to put Y down here. I'm going to show you what I mean by that. Let's make up a matrix A, and it'll be 2, 1, 4, 0, negative 1, 1, 1, 1, 1, negative 2, 0, 0. Okay? So I've made a 4 by 3 matrix here. I said I did this wrong when I said this was length. This was length n. This is length m. Sorry. This is part of why I like the diagram, because it helps with this, I think. Okay, and then I'm going to make up some vector x that's going to be 3 vector. So let's call it 1, 2, 3. Sure, that's fine. So here's my A, here's my X, and my output Y I'm going to put here. And this multiplication, you go through each row and you essentially do the inner product of each row of A with X. So for each I going down the rows, I'm going to sum up the X vector with K. So so in this case, it's going to be 2 times 1 plus 1 times 2 plus 3 times 4. And maybe I'll, can I do it like this maybe? So I say 2 times 1 plus 1 times 2 plus 3 times 4. Like this. I don't know why I have so much trouble with that. And we add those together. And so in our case, we get 2 plus 2 plus 12, 16. Right? Did I do that right? That's the first element of y. And then the same thing for the next one. I'm going to do 0 times 1, 0, plus negative 2 plus 3. Negative 2 plus 3 is 1. Right? And then this one, 1 times 1, 2, 3. So 1 plus 2 plus 3 is 6. And then this one is negative 2 just by itself, negative 2. Okay? So each element of y is the inner product of that row with x. Okay? And you can kind of see now, I drew all over this, so I'm going to erase some of these. You can kind of see now why I had the lengths wrong before and why they have to line up the way they do. The length of x has to match the number of columns of A, and the length of y has to match the number of rows of A, right? And And so in general, if you have an m by n times an n by 1, you end up with an m by 1 thing. And we can come back to that more when we talk about matrix vector. Matrix multiplication, sorry. Yes, so, okay, so this is matrix vector multiplication. And, I mentioned that about the inner product. Now we're at a point to understand why we've been using that transpose the whole time, because if I have some vector x, right, say, 1, 2, then x transpose is this 1, 2, this 1 by 2 matrix, right? And so, so for example, x transpose x would be 1, 2 times 1, 2, and it is the inner product. It's this one single thing, and the output that we get is a 1 vector, or just a number. In our case, 1 plus 4, 5, right? Yeah. So this x transpose x, you can actually read it either way, as either the inner product of two vectors, or as treating that first x as a matrix, an n by 1 matrix, taking the transpose and then doing a matrix vector multiply on it. And so that's kind of our idea of why we use that transpose there for the inner product. Okay, so let's talk a little bit about some properties and some examples, and kind of walk through a little bit here. Well, one thing is that if you have the 0 vector, right? So if I had some a times some 0 vector, that's going to be 0. Not necessarily the same 0 vector, right? It could be different lengths, as in this example. If these were all zeros here, of course all these would get multiplied by 0, and then I would have zeros here. But in that case, y would be a 4 vector of zeros, and x would be 3 vector of zeros. So it's not the case that they're the same necessarily. Again, if this is m by n, this will be an n vector of zeros, and this will be an m vector, length m vector of zeros. If you have an e, a unit vector, so let's say I have a times ej for some j. Okay, well, what is that going to look like? So imagine here I did, let me get rid of all these zeros now. I'll keep my matrix the same, but I'm going to get rid of my x's. I'm going to change them. I'm going to change all this to, and these. Maybe I should have copied it. Next time I'll try that. But anyway, so imagine I had something like, say, 0, 1, 0 here. Have a unit vector. Well, I'm going to get, in the first spot, 0 plus 1 plus 0. In the second spot, 0 plus -1 plus 0. In the third spot, 1. 0 plus 1 plus 0. In the fourth spot, 0. So you can see I got the exact second column there, right? This column right here. And so in general, if you have some a times unit vector e sub j, you're going to get back the jth column, if you want to call it a sub j, the jth column of that matrix. And in fact, this kind of opens up a different way of thinking about this relationship here. So So I said each yi is equal to the sum of aik xk, right? And if you think about each ai as a row, right? If you think about each ai as a row, first row, second row, third row, then this is exactly the kind of like inner product way of thinking about it that I was just talking about. That each individual element in y is going to be the inner product of the ith row with x, right? So if I can I can say something like, maybe I can rewrite it as something like yi is equal to, I almost kind of want to write something like ai transpose xk, except that doesn't really work because this single index on the matrix is kind of a tricky concept to get across here. But you can imagine if there was some way I could say to take the ith row, maybe I say something like ai star or something, like ith row every column. Then I get that. Then I can sort of use that inner product definition. But there's another way of thinking about it that's actually just equally valid and comes in handy just as much, which is that if y is a times x, then that means that that y is the sum going the other way in some sense of it, where I would say I want to get the ith, I want to get the kth column. So let's say star every row. I'm going to get the kth column, and then x sub k. So in other words, I can also think about if I rewrite my matrix A as a set of, this is actually how I should have done it in the first place instead of not doing the stars, but that's okay. Imagine that I think of this thing as a set of columns, A1 ... A n, right? Then y is a1 is the scalar x1 times a1 plus the scalar x2 times a2 plus ... xn an. In other words, it's the linear combination of all of the columns using x as the coefficients of the linear combination. So, going back up here, like another way to think about this whole thing, before I was thinking about it like it's a sequence of inner products of each row. But there's another way I can think about it that will make just as much sense or more sense depending on the context, which is that it's the linear combination of the columns and each coefficient. Well, I guess I can leave that little line there. Is in x. So for example, let's take away these and put all ones in there. So let's say x was 1, 1, 1, like that, right? Right? this is going to be, I could do it as the inner product, 2, 1, 4, 2 plus 1 plus 4, and get that first element. But another way to think about it would be that I'm going to get 2 times 1 here, 0, 1, negative 2, and then I'm going to add in fact, let me make them a little bit different just so that we can, let me make these numbers a little bit different. Let's make this one, how about negative 1, and we'll make this one 2. I have no idea if this is going to work out or not, but I can start by taking the first column, and then I just do negative 1 times the second column, and I add that one in. So I'm going to subtract a 1 from this. So it'll be like this, plus negative 1 times 1 minus 1, 1, 0, plus 2 times 4, 1, 1, 0, like that. And let's see if I can kind of just like move that 2 over. Okay, perfect. And so this process is going to give us the exact same answer as if we did it the inner product way, because it's going to be, x1 times 2 plus negative 1 times 1 plus 2 times 4 in the first slot. It's just sort of a different way of thinking about it, that it's this linear combination of the columns. And like I said, both come in handy sometimes. It's just a matter of which one is most useful for thinking about it. Okay, so a couple other things I wanted to consider while we're here. Properties of this thing. So we mentioned already that multiplying it by the 0 vector looks like you would expect, right? If you have some u plus v, it distributes out also, and you can check this. You can check this just doing the proofs of the sums. It's not very difficult to prove. You get a times u plus a times v, and this I think it's almost deceptively simple. Like, it's true, but it almost looks like it should be like trivially true because we have this distributive property all the time, so why wouldn't we have it this time as well? But you do have to think, like, there's actually something kind of complicated going on here. On the left-hand side, I'm adding together 2 vectors, getting a vector, and then doing this vector matrix vector multiply. But in the other one, I'm doing 2 different matrix vector multiplies and then adding them together with a vector add at the end. So like computationally, they're quite different, which is more efficient. This one is more efficient because you are only doing one matrix vector multiply is cheaper. Which reminds me, side note, how expensive is this thing? How expensive is it to do a matrix vector product? Well, you have to do m times n approximately, m times n operations, right? Because for each row, for each column, you're multiplying them together, right? If you had an n by n matrix, it would be approximately n squared. Yes, okay. But so that is true that they distribute out like this, and it works for matrices also. So if you had, on the other side, if you had a plus b times u, that's the same as au plus bu, like that. But commutativity and associativity not work the way we might expect. In fact, they don't work at all. So, for example, maybe we'll just start with associativity. If I try to do something like, okay, I'm going to say a times the vector u, and then multiply it times the vector v, like that, right? Is that going to be equal to? A u v? Well, alarms should already be going off in your head because we can't do this. We said that back when we did vectors, we can't just multiply two vectors together. We can do the inner product of two vectors, but that wouldn't work. That wouldn't be the same as this at all. And in general, this is, you know, go red here. This is a big red no. Nope, not allowed. And similarly, if let me go back to green now. Is this green I'm looking for? Something like that. Similarly, I might be tempted to try something like AU equals UA. But this one is also a no-go. And again, it's because we want to preserve the properties for matrix multiplication. We kind of said, like, with scalar multiplication, it's fine. You can do it wherever. But this is also not good. And this this is no good right here. Not allowed. You can't multiply from the left like that with a vector. It has to be this one. And we'll see once we get a little bit more into matrix multiplication, we'll see why that is. But yeah, so this sort of distribution works the way we would expect, but you can't commute or associative. It's not commutative or associative, so you can't do that. And yeah, this kind of, I'm sure there's more that we'll come across as we work our way through, but this was kind of our big picture here. Matrix vector multiplication. It's extremely exciting. All right.